Hello everyone, I am Sanjay De, an MSc final year student at the Department of Physics, IIT Kharagpur. And today I am going to teach you one of the most important topic for the JEE Mains and JEE Advanced, and that is known as photoelectric effect. So this is the outline of the lecture. In this lecture I will talk about the historical background, the experimental study of photoelectric effect, Einstein photoelectric equation, and at the last a numerical based on the equation. So let's start. So, in 1887, German physicist Heinrich Hertz discovered the photoelectric effect during his electromagnetic wave experiments. So, he observed that a metal surface, whenever a metal surface is illuminated by a UV light, then some negatively charged particles were coming out of the surface, and these negatively charged particles were basically electrons, and these electrons were named as photoelectrons, and this phenomena is known as the photoelectric effect. Later on, two other physicists, Haloax and Leonard, also investigated this phenomena detail. From their experiment, they found that if you have a metal plate and if you illuminate any frequency of light, then no electrons will be come out. You have to give a minimum frequency of light, then electrons will be coming out of the surface, and this frequency is known as the threshold frequency, and this threshold frequency basically depends on the metal or the photosensitive material, and it is denoted by mu 0. Okay, so this was all about the historical background of the photoelectric effect, and as I previously told that the ejected electrons were termed as photoelectron. So let's move on to the next part. So this is the experimental study of photoelectric effect, and this is the schematic diagram for the experimental setup. So here this is a light source whose frequency and intensity can be varied, and this is the quartz window which helps to pass the light to the evacuated glass tube, and this is a photo sensitive plate on which if a light of certain frequency falls, then electrons will be ejected out, and this A plate is basically to collect the ejected electrons, and this using this commutator we can change the polarity of C and A plate, and there is a constant voltage source to collect these electrons at A plate, and there is a ammeter. This is used to measure the current. If any electrons ejected from the C plate and collected to the A plate, then we will get a current. From that we can say that photoelectric effect is observed. Okay, so this experimental arrangement can be used to study variation of photocurrent with different parameters like intensity of radiation, frequency of radiation, and the potential difference between A and C plate. Okay, so let's see what are the graphs obtained from this experiment. So in the first graph we observe that the photoelectric current is linearly proportional to the intensity of light. I mean, if you have higher intensity of light, you will get more photoelectric current. That means if your intensity is increasing, that you will get more number of photoelectrons per unit time. So this was the first graph, and the second graph that was obtained when the photocurrent versus collector potential was measured, keeping the frequency, I mean the frequency of the light that was illuminated was kept constant, and in this graph it was taken at different intensities. So as I previously told that if you have different intensity, then this graph the photo current will be also different. So as I3 greater than I2 greater than I3, so their photo current will be also greater. Okay, and this is the stopping potential. What does stopping potential means? Stopping potential is means like this is the C plate, this is the A plate, and electrons are ejected out from this plate. So if I change the polarity of the plates, if I change the polarity of this plate negative, so the maximum potential, so that no electrons can come out to the A plate. I mean the photocurrent I photocurrent becomes 0. So whenever we apply the maximum retarding potential, the photocurrent will be 0, and this is known as the stopping potential. Okay, so the stopping potential is denoted as minus V0. As we keep the frequency constant, so the stopping potential is also constant, because for a certain frequency the maximum kinetic energy of the electrons will be also constant, there will be no change. So to stop the maximum maximum kinetic energy of the electron, you need a V0 potential. But in the third curve we see we kept the intensity constant, and we take at different values of illuminated light this curve. So nu 3 greater than nu 2 greater than nu 1, and we got different retarding potential, because as the frequency of light, let's say these 2 and 3, as nu 3 greater than nu 2, so the kinetic energy for these frequency and the kinetic energy of electrons for the frequency will also greater. To stop the greater kinetic energy of electrons, we have to give greater potential, greater retarding potential. That's why V0 greater than the magnitude of V0 3 V0 2 is like this: V03 greater than V02 greater than V01. So this was all the experimental curves. Now let's move on to the next topic, that is Einstein photoelectric equation. So before 1905, Leonard Walhacks and Arj, they everyone did many experiments, and there was no equation to explain this photoelectric effect. Everybody performs experimental, and uh, they published their experimental observations, but there was no theory for this photoelectric effect. So Einstein came with a new picture of EM radiation to explain this photoelectric effect. He said that the light or radiation is consist of different discrete packets of energy, and that is known as photons, and that is called photon. So this is one photon, this is one photon, this is one photon, and each of these photon has an energy E is equal to h nu, where h is the Planck constant, this is the Planck constant, and this is the frequency of the light. And the momentum of these photons is p equal to h by lambda, where lambda is the wavelength of the light. Okay, so you can also express this E equal to hc by lambda. So both of these relation can be used to measure the energy of photon. Now Einstein explained that whenever light strikes on the metal surface, the photon transfers their energy to the electrons to the metal. So let's say this is a photon, and whenever strikes the electron, then this energy is transferred to the electron, and if the photon has enough energy, then the electrons will be come out of the surface. So the photon's energy should be greater than the work function of the metal. So what is the work function? Work function is the minimum energy required to remove an electron from the surface, and it is denoted by phi, and it basically depends upon the metal or photosensitive material, what type of material. If you have a sodium sample and if you have a potassium sample, for both of their work function will be different. Okay, so their work function will be different, so you have to, your photons will must be greater energy than the work function of the material. So using this assumption, Einstein gave his photoelectric equation, and that is h nu is equal to phi plus ke max, where ke max, as I previously told, that this is the maximum kinetic energy of the photoelectrons. Okay, but there might be some electrons whose kinetic energy will be less than this kinetic energy, but we will take the maximum kinetic energy, and this maximum kinetic energy is equal to the EV0. EV0 is the stopping potential. I mean the EV0 is the energy required to stop the maximum energetic photoelectrons. That's why we have taken Ke is equal to EV0. So this equation can be write as H nu is equal to phi 0 plus EV0. And if we want to write it in the terms of half mv square, as we know that kinetic energy is equal to half mv square or p square by 2m, then we can also write it like this. And we can also write it in terms of wavelength. We can substitute h nu is equal to hc by lambda whenever we need in our numerical problems. Okay, so if we plot this curve, this is a linear curve. In the y-axis we have taken maximum kinetic energy, and here we have taken the frequency of the illuminated light. Then the slope of this curve will be coming like h, as you can see that Ke equal to h nu minus phi. Okay, so this is the slope and this is the intercept. So this is equal to minus phi, and at nu equal to nu 0, the kinetic energy will be 0. I mean the maximum kinetic energy photoelectrons will be 0, and that is, and then the equation will be equal to h nu 0. So nu equal to phi by h. Okay, and this nu is basically known as the threshold frequency. This is known as the threshold frequency. So this was all about the theoretical part of the photoelectric effect and the Einstein equation. And let's move on to the numerical based on this equation, which was asked in the JEE Advanced 2014. So let's read the question. So the question says, a metal surface is illuminated by two different wavelengths of light, 248 nanometer and 310 nanometer, and the maximum speeds of the photoelectron corresponding these wavelengths are u1 and u2, and the ratio is given 2:1, and the hc is given 1240 electron volt nanometer, and the work function of the metal is nearly which one of the following options. Okay, so we have to first think which equation we have to use to calculate the work function. So we can see that u1 and u2 value is given, so it is obvious that we have to use this equation, because these equation consist the velocity of the photoelectrons, and the velocity of photoelectrons is given, so we have to use this equation. But we have to use this equation in terms of wavelength. So let's write for the first case. It is given 1240 248 nanometer. So hc by lambda equal to phi into half m. For this it is u1, so we have to write u1 square, and hc equal to 1240, and this is 248 equal to 5 plus half m u1 square. So this is 248, and 1240 by 248 is 5, and this is half m u1 square. And for the second case, same thing, and in this case we have to take u2 square, and here the wavelength of light is given 310, and phi equal to half mu2 square, and this comes out 4 plus phi 0 into half mu2 square. So let's say this is equation 1 and this is equation 2, and if we divide this equation like this, right, if mu1 square and 4 minus phi equal to half mu2 square. So if we divide 1 by 2, then we will get minus 5 minus phi by 4 minus phi, and half m will be cancelled, and we will get u1 square minus u2 square, and u1 is to u2 was given 2:1. So this is 2 by 1 whole square equal to 4. So from this we can get 5 minus phi equal to 4 into 4 minus phi. So I am writing this here. So we will get that 5 minus phi equal to 16 minus 4 phi. If you take this 3 phi equal to 11. Okay, so phi equal to 11 by 3 electron volt, which is equal to 3.666 electron volt, and we can approximate this to 3.7 electron volts. So the option A is correct. So the phi is equal to 3.6 electron volt. So this was a very good question from the photoelectric equation. So that's all about the today's lecture, and thank you.